Hello and welcome back. In this slice of physics, we're going to discuss a specific application of electric fields, specifically the parallel plate capacitor. We will first discuss what a parallel plate capacitor is, what are its properties, and then we will talk about the electric field between the plates of a parallel plate capacitor. We'll focus on the magnitude of the electric field, the direction of the electric field, and some of its properties between the plates. First, let's discuss what a parallel plate capacitor is. Well, it's just two plates that are metal plates that are separated by a distance. So I'm going to take these two as the plates that are parallel to each other, separated by a distance. And if I were to show the third dimension, these might be rectangular plates, they might be square plates or circular plates. It doesn't matter what shape they are, but they do have an area. So I got two parallel metal plates. They have an area A. The area of each plate is A. We will always work with examples when the two plates have the same area. And since we're talking about electric fields, we must talk about charges. And in a parallel plate capacitor, the charges on the two plates have opposite signs. So if I have a charge of plus Q on one plate, that is the positive plate, I would have a charge that's correspondingly negative Q on the other plate. A thing to note here is the Q is the same on both the plates. So if I have plus 2 nanocoulombs on the positive plates, I would have a minus 2 nanocoulombs on the negative plate, and so on. Those two numbers will always be the same. The reason that makes sense is we typically start with neutral plates. Both these metal plates would be neutral to begin with, so there is no net charge on either. And then we just move charges from one plate to another. And typically, since we move negative charges from one plate to another, moving a certain amount of negative charges from this left plate to the right plate will leave the right plate with a net negative charge, and because those negative charges left the left plate, it'll leave this plate with a positive net charge. The third thing you have as a property of a parallel plate capacitor is the distance between the plates. So the two plates are parallel to each other and separated by a distance d. One more clarification for parallel plate capacitors. For our logic to work with how we will discuss these, the area of the plates is significantly larger than the distance between the plates. The reason for that is we will focus on what happens between the plates kind of in the intermediate area, so over here, and we will not consider edge effects. It'll become quite clear to you in just a minute as to why we don't consider edge effects. But when we have dimensions of the plate significantly larger than the distance between the plates, for most of the plate, you are not going to be anywhere near the edge, so you are good. Okay, to discuss the electric field between the plates, I'm going to go back to a one-dimensional view. So I'm going to redraw this parallel plate capacitor over here and just look at it edge on so I don't see that third dimension. So I've got this as the positive plate, so there's going to be positive charges lining up over here, and I'm going to have correspondingly negative charges lined up on this right plate. And we want to discuss the electric field at a couple of points. We'll first discuss the electric field at a point A over here close to the positive plate, and then we will talk also about the field at a point B that's closer to the negative plate and see how they compare. Okay, first of all, we know that the electric field at any point is the vector sum of the electric field from all of the charges that are responsible for creating the field at that point. And we have done some practice with a couple of charges. We had two charges and we determined the net electric field from two charges. Now we are going to conceptually, without working through the numbers, we're going to conceptually discuss the net electric field at point A from these 1, 2, 3, 4, 5, 6, 7 positive charges and the 7 negative charges. So there's 14 charges for which we need to determine the net field at point A. Okay, given that this point A is right in front of this positive, central positive charge over here, the electric field from that charge will point directly away from it. It points away from positive charges and towards negative charges. So then as I move up, the second charge over here would have an electric field at A that points directly away from that charge. So something like that, and it won't be quite as long as the first electric field because this charge is farther away from A than the central charge was. And then I move on to this third charge. that's going to have an electric field at A pointing directly away from it and smaller still, and so on for the fourth charge and other charges that are lined up over here. And then as I go below the charge, this charge over here would have an electric field at A that points like that away from it and about the same magnitude as the one from the charge above the central charge. And then as I move on to the next one, once again, it would point directly away from it and point something like that and be shorter. And this is where the edge effects become relevant. We took a point in the center so that we don't worry about what happens at the edges. And if the dimensions of the plates are in reality much bigger than the distance between them, which is how they would be, any point that I take will have equal number of charges above it as it would below it, roughly. And so it would have electric fields that point like that. Okay, so now let me take a quick detour and see what the net of all of these would be. I'm going to magnify the details of that over here. So I had that, and that as my 5 electric fields. And there would be many more like this. The point is there's going to be a symmetry established if there are a roughly equal number of charges above it and below it. That's why we don't go near the edges, so we always have the symmetry. Now, how do these add up? To add these two fields over here, I have to do my geometric add where I can slide this bottom field so that its tail lies on the tip of the other charge, so it goes there. So the net of these two fields on each side of the central field would end up being also something that points straight to the right, like the central field did. Similarly, if I take my next two charges, I can take this bottom one over here, slide its tail to the tip of the first one, and I also end up with a field that points straight to the right. So if I have this symmetry, the vertical components of all of these vectors will cancel each other. One of them is pointing up, the other one is pointing down. They're both equal in magnitude. So the vertical components all cancel each other, leaving only the horizontal components. So the net electric field would be the sum of this long arrow, this arrow, which was the sum of the first order flared electric fields, plus this little red arrow over here, which was the sum of the second order flared electric fields. But the point is the net electric field at point A is going to point straight to the right and be pointing something like that. That would be the net effect of the field from all the positive charges. What happens from the negative charges? Well, just like there was a positive charge to the left of point A, there's going to be a negative charge to the right of point A. Let's ignore this little offset that I've drawn over here. And so the electric field from that negative charge will point at A toward the negative charge. So it'll be a repetition of what I did with the positive charges, although the arrows will be shorter because point A is farther away from the negative charges than it is from the positive charges. But qualitatively, you're going to have a very similar diagram. And the end result of all of these will also be something that points to the right. So let's call this E negative. This is E positive. So the final net electric field at point A from all of these 14 charges will be something that points to the right like that. And since I'm not zoomed in anymore, the length has shortened to be the sum of E plus and E minus. So let me show that as the electric field at point A, which I have offset a little bit to the bottom over here. Next, let's see what happens at point B. As I move from A to B, I'm moving away from the positive charges. So the effect of those, the electric field from all the positive charges, will drop. They won't be as strong as they were at point A. They would be weaker. But on the other hand, I'm moving closer to the negative charges. So the effect of the electric field from the negative charges will grow while the electric field from positive charges decrease. And so the net effect ends up being that the electric field at B equals the electric field at A, which means it would have the same length and same direction. So it would look something like that. Remember, even though the arrow goes beyond the plate, that's not telling me anything about the electric field to the right of this negative plate. This arrow is only telling me what the electric field is at point B. Just like this arrow here was just telling me what the electric field at point A was, even though I offset it just to show the arrows more clearly. So the vectors only show the value of the field at the one point, and they don't say anything about what it is at this location or this location. They only give you an indication of what it is at point B in this case and point A in this case. So let's put all this together and summarize some of the key observations that we have qualitatively justified over here. The first thing is that electric field between the plates of a parallel plate capacitor is uniform. What we mean by that is that it is the same everywhere between the plates. So EA is the same as EB, and if I pick any points between the plates of the parallel plate capacitor, so as long as we don't get anywhere close to the edges and we remain in the center, which is easy when you have plates that have large dimensions compared to the distance between them, then at all of those points between the plates the electric field is the same. Second, we see that the electric field is perpendicular to the plates and points directly from the positive plate to the negative plate. So in this case, since my positive plate was to the left and negative plate was to the right, the electric field at all points between the plates of the parallel plate capacitor will point from left to right as shown here. Okay, qualitatively, those are the key observations. Now let's talk about what the equation is and what the electric field is compared to some of the dimensions and the charges on the plate. It turns out that the electric field between the plates of a parallel plate capacitor is given by this equation, Q over epsilon naught A. I'll describe every one of these variables, but this only gives us the magnitude. So because electric field is a vector, I also need to specify the direction, which I would say positive to negative plate. Okay, now let's study this equation and make sure we know what the different parts of it are. The left-hand side is just the electric field between the plates. Any location between the plates. That's going to be the electric field at point A, at point B, and at any one of these points between the plates. Q at the top here is just the charge separation between the plates. So one of the plates would have a charge of plus Q, the other plate would have a charge of minus Q. So for example, if I have plus 30 nanocoulombs on a positive plate and minus 30 nanocoulombs on a negative plate, then Q in this case would simply be 30 nanocoulomb, because this is plus Q, so Q is 30 nanocoulomb, and this is minus Q, so Q is still 30 nanocoulomb. Epsilon naught is a constant, and it's a new constant that we're introducing, and it happens to be related to the previous constant we met. Epsilon naught is simply 1 over 4 pi k. K is the same old Coulomb constant that we met before, and so these constants are related in this sense. And so we can see that epsilon naught would simply be 1 over 4 pi times 9.0 times 10 to the 9 Newton meter square per Coulomb square, which ends up being 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. A, as we discussed, is the area of the plates. Both the plates have the same area. So this equation tells us that if I separate more charges between the plates, if I put a bigger amount of positive charge on one plate and a correspondingly big negative charge on the other plate, my electric field between the plates will increase. And it also tells us that the electric field is inversely proportional to the area of the plates. So for the same charge, if I make the plates smaller, the electric field will become bigger. And if I make the plates bigger, the electric field will become smaller. The third thing that we see here is I gave you another property of the parallel plate capacitor, which was the distance between the plates, and that does not figure in this equation. So this tells us that the electric field between the plates of a parallel plate capacitor is independent of the distance. That's an important observation. For example, by moving this negative plate over here and change the distance between the plates by reducing them, it doesn't have any effect on the electric field between the plates. Lastly, let's see if the units work out for this equation. We're going to take the right-hand side and work just the units of these quantities. Numerator is Q, which is the total charge separation between the plates, and that's got a unit of coulombs. The denominator has epsilon naught, which has the units of Coulomb squared over Newton meter squared. and the area would have a unit in SI units of meter squared. Now you can see that this meter squared cancels this meter squared. This coulomb will cancel and just become 1 at the top, and it'll cancel one of these coulombs at the bottom, so the 2 will go away. So I ended up with 1 over Coulomb over Newton, which is the same as Newton over Coulomb, which is our unit of electric field. So we're good with the equation working in terms of units. Alright, since we discussed a number of things about the parallel plate capacitor, let's summarize the different properties. We are interested in discussing the electric field between the plates of a parallel plate capacitor. We don't talk about the electric fields beyond the plates, and in fact it turns out that the field beyond the plates is much smaller than the electric field between the plates, so we focus on the field between the plates. First, the electric field is uniform between the plates. It's the same everywhere, same magnitude, same direction. In terms of magnitude, we saw that the electric field is directly proportional to the charge separation between the plates. Higher the capital Q, higher the electric field. We saw that it's inversely proportional to the area of the plates. Bigger the A, which is the area of each plate, smaller the electric field between the plates. And thirdly, maybe somewhat surprisingly, we saw that the electric field between the plates does not depend on the distance between the plates. So that's all about the magnitude of the electric field. In terms of direction, the electric field points from the positive plate to the negative plate. Those are our key points about how the electric field works between the plates of a parallel plate capacitor. Thanks for watching, and I'll see you soon.